SwayamPrabha. Digital India. Educated India.
In the previous lecture, we looked at how to set up governing equations of motion for using Hamilton's principle, and we defined a quantity known as Lagrangian, which is the difference of kinetic energy and potential energy, and we defined an integral known as action integral, and according to Hamilton's principle, motion takes place in such a way that this action integral is rendered minimum. So, a condition for stationarity of this action integral is obtained through this equation, or obtained as this equation, and this is known as the Lagrange equation. Now, we applied this principle to simple dynamical systems like a 2 degree of freedom discrete multi-degree freedom system. We set up the expression for the Lagrangian in terms of kinetic energy and the potential energy, and we showed that approach leads to a pair of second order ordinary differential equations which are coupled to each other. Now, this pair of equations could as well be obtained by drawing free body diagrams of M1 and M2 and using D'Alembert's principle. But this is a different approach where we deal with only scalar quantities like energies, not the vector quantities that we will be using if we were to use D'Alembert's principle and draw free body diagrams and so on and so forth. Now, what we will do, we also covered the case of an actually vibrating rod, how the Hamilton's principle can be applied. So, here the action integral is obtained as an integral over the domain of the rod, that is integral 0 to L m u dot square dx, and this is the strain energy and this is the action integral, and by using the calculus of variations we obtained this as the field equations, and I also pointed out that the variational approach also leads to the definition of the appropriate boundary conditions, and the 4 generic actually vibrating rod problems where the 2 ends are free, one end is fixed and other end is free, and both ends are fixed are obtained as the appropriate boundary conditions for these 4 cases are obtained as a part of this solution. Now, what we will do in today's class is we will extend this example the approach to a few examples on actually vibrating rods, and then we will apply the method to the problem of flexural vibration of beams. So, the few examples that now I will consider helps you to analyze apart from setting up the field equations, we will also obtain the appropriate boundary conditions. The emphasis is on obtaining the boundary conditions. So, here we have a actually vibrating rod which is mounted on a spring here, and at this end it carries a mass through a spring as shown here. Now, the kinetic energy of this system consists of kinetic energy stored in this bar and the kinetic energy of this mass, that is written here. U of x comma t is the actual displacement of this bar and V is the displacement of this mass. So, we get the kinetic energy as shown here. The potential energy is a contribution from strain energy stored here and the energy stored here and energy stored here, and that is written in this form. Now, the action integral is obtained in terms of the energy stored in the various elements, and that is as shown here. Now, in this example I will run through the various steps again. So, we will assume that u of x comma t and v of t are the unknown optimal solutions, and u bar of x comma t and v bar of t are the class of admissible solutions which are obtained by adding the variation one variation eta 1 x comma t, other one eta 2 of t to u and v respectively. So, now the action integral is now parameterized in terms of the 2 parameters epsilon 1 and epsilon 2, and we get this equation. Now, we know that the action integral would reach the stationary value, the necessary condition for that is the gradient with respect to epsilon 1 must vanish and gradient with respect to epsilon 2 must vanish. And we know beforehand that this stationarity condition will be realized when epsilon 1 is 0 and epsilon 2 is 0, and similarly epsilon 1 and 2 are 0, because by definition u and v are the unknown optimal solutions. Now, if I implement these two requirements, we will get these two equations, and here we have now terms involving time derivative of the variation and spatial derivative of the variation. The time derivative appears here as well as here in the second equation. So, we will deal with these three integrals first and then come to the other part of the equation. Suppose if you now consider T1 to T2 m u dot eta 1 dot dt, I will integrate by parts and I will get the first term is this and the second term is this. Similarly, on terms involving spatial derivative of the variation, we again integrate by parts. This is the first term I get, this is the second term. The second equation for the variable v dot of t, there is a eta 2 dot of t, and integration by parts now leads to these two terms. Now, eta 1 x comma t and eta 2 of t are arbitrary variations, and eta 2 of t is 0 at t 1 and t 2. So, what happens is these two of these terms go to 0. See, these terms are appearing here and here, these two are 0. Now, we need to deal with the other terms. Now, reverting back to the original equation, I get now the statement for stationarity of A as this equation. And we have to now collect terms involving eta 1 of x comma t, which is done here, eta 1 of 0 comma t and eta 1 L comma t, and if we organize these terms, we will get the field equation. Since eta 1 x comma t is arbitrary, eta 1 L comma t is arbitrary, eta 1 0 comma t is arbitrary. The only way this sum can be 0 for all eta is that individual terms must be 0, and using that condition I get this as the field equation and these two as the appropriate boundary conditions. So, these boundary conditions, for example, at x equal to L now involve the force transferred through this spring, and x equal to 0 the force transferred through K1, as you can see here. Now, similarly for the point mass, if we do this if we use the second equation, we get the governing equation to be this. This we have seen earlier for a simple single degree freedom system. So, the final equations, these two are the field equations, these two are the boundary conditions, and we have to specify the appropriate initial conditions to solve the problem. So, the point that we can take from this exercise is that the variational method helps you to correctly identify the boundary conditions along with the derivation of the field equation. So, I will run through a few more examples. I will not work out all the steps in detail, but I will mention. So, this is one example where a spring K connects the two ends of the rod. So, now strain energy will be given by strain energy stored in the bar and the energy stored in the spring as shown here. This is the strain energy stored in the bar and this is the energy stored in the spring. This is the kinetic energy, this is only the energy stored in the bar. So, this is the Lagrangian, and if we apply now the variational argument, we get the field equation to be this remains same as what we got earlier, but the boundary conditions now at x equal to 0 will have this additional term, which is the force transferred through this spring at this end, and similarly at x equal to L I will get another force, which is the force transferred at this end through the spring. Now, how about an inertial element being present at the boundary? Suppose if I have now a point mass at the end, and again now the kinetic energy will consist of the energy stored in the bar plus the kinetic energy of this mass which is given here, and the strain energy will be the energy stored in the bar. So, this is this expression. So, if you apply the Hamilton's principle, we will get this as a field equation. Now, at this end the bar is fixed, this is a boundary condition. At the other end, now the axial thrust due to elastic action has now there is an additional term which is due to the inertia of this mass. So, that will appear in the boundary condition. So, along with this, of course, we need to specify the appropriate initial conditions. Now, slightly more involved example. Now, there is there are two springs and another inertial element. This is an exercise that you need to do. The hints are given here. This is the expression for the kinetic energy. This is the expression for the potential energy, and I have worked out few steps. If you work through this, you will get the field equation, the equation of motion for the discrete mass, that is this is given by this, and for the bar this is this, and the boundary conditions, as you can expect, there will be a term involving the force transferred through the K1 at this end and a term involving force transferred through K2 at this end. So, that is what you see at L equal to T, there is a force through K2, and at L equal to 0 there is a force through K1. Now, this logic can be extended now to other structural elements like Euler-Bernoulli beam, plates and plane stress elements and so on and so forth. So, for purpose of illustration, I will consider one example, that is case of a Euler-Bernoulli beam. So, this beam has span L, flexural rigidity E I of x and mass per unit length m of x. The kinetic energy is given by this expression m of x into v dot square dx. I am considering the underlying beam theory is the Euler-Bernoulli beam theory, therefore, there is no contribution to kinetic energy from rotary inertia. Similarly, when I write potential energy, this is the strain energy due to bending, and there is no contribution to this energy from shear deformation. So, if you include rotary inertia and shear deformation, we will get the corresponding formulation for a Timoshenko beam. But right now, we will focus on Euler-Bernoulli beam, and this is the Lagrangian T minus V, and this is the action integral. So, we can see that the Lagrangian is now a function of V double prime that appears here and V dot which appears here. So, I can write action integral in terms of this function as f of V double prime V dot. Now, as before, we consider this to be the unknown optimal solution, and this is the variation, and this is the class of admissible function which have now been parameterized in terms of epsilon. So, A as a function of epsilon is this. Now, we know that optimal value of A as a function of epsilon is reached when epsilon equal to 0. So, we apply this condition. So, dA by d epsilon is dou f by dou epsilon, which will be dou f by dou v double prime into eta double prime plus dou f by dou v dot into eta dot. So, the bar we are not maintaining distinction between V bar and V, because this calculation is being done at epsilon equal to 0, and in which case V bar and V are identical. So, this is the equation. Now, we again consider these two terms separately. So, we have 0 to L dou f by dou V double prime eta double prime x comma t. So, one integration by parts will lead to this equation, and on the second equation we will again perform another integration by parts. So, I will end up with these three terms. Similarly, the if you consider this term and consider integration from T1 to T2, we get again integration by parts, we get these two. Now, at t equal to T1 and T2, the variation is 0. So, this term drops off. So, we have to still interpret the other terms which will still remain till we complete their interpretation. So, we carry them further in our derivation, and we get this is now the equation which is a condition for stationarity of A. Now, we will again use the arguments that variation is arbitrary Therefore, the only way this term can be equal to 0 is when each of these terms are individually equal to 0. So, since eta of x comma t is arbitrary, the term inside this brace must be equal to 0, I get this, and similarly term inside the bracket must be 0 and term inside this bracket must be equal. So, now this is still that f is remaining, the notation for f is this. So, if you now insert all these calculation dou f by dou v double prime, dou f by dou v dot etcetera in this, you will get the field equation, which is the well known Euler-Bernoulli beam equation. This is the field equation. Now, the boundary conditions are to be derived from these conditions. Now, at free end, when displacements are not specified, we will not be able to assign any value to the variation. Therefore, the term that multiplies that must be equal to 0. So, at a free end, neither displacement can be specified nor slope can be specified. Therefore, for this term to be equal to 0, it is natural that this multiplier must be equal to 0. So, on the other hand, at the if at the x equal to 0 or L, if displacements are specified, for example, in a simply supported beam the translation is specified to be 0, in which case this will be 0, and similarly at the fixed end the slope will be 0, therefore, this will be 0, the variation would be 0. So, we can there are now 16 combinations of one span beams that are possible, and I have just displayed them here. This is both ends are free, this is one end is fixed, other end free, and so on and so forth. So, now we can examine, suppose we are focusing on one of these boundaries and I look at this boundary and consider these expressions, we can see here that the slope cannot be specified, therefore, E I v double prime must be equal to 0. We know that E I v double prime represents the bending moment is 0, and similarly the shear force is 0, which comes from this equation, because displacement cannot be specified. So, this is 0. At the clamped end, we know that the displacement is 0, therefore, the boundary conditions emerge as v prime equal to 0, v equal to 0, which again satisfies this equation, because the variation must satisfy these conditions. Similarly, it is simply supported end, the bending moment is 0 and the displacement is 0. At this roller end, the slope is 0 and shear force is 0. So, we can therefore see that consistent with the variational formulation, we can think of 16 possible single span beams and we can set up all the appropriate boundary conditions. Now, slightly more involved example, suppose an Euler-Bernoulli beam is resting on a Winkler's foundation and it also carries an axial load P. Now, what is the kinetic energy? The kinetic energy will be due to flexure of the beam, and this is given by this. The potential energy now will be due to the flexure of the beam and due to the elastic foundation and contribution from axial loads. So, if we write these expressions, this is flexure, this is from Winkler foundation, and this is due to the axial compression load. So, we can form the Lagrangian and again construct the action integral. Now, the f function, that is the Lagrangian, now has because of Winkler foundation and the axial loads, we have now in addition to v double prime and v prime, we also have v and v prime. So, we can do this, we get this as the Euler-Lagrange equation, and the field equation turns out to be this. And the boundary conditions now will involve, for example, at the two ends the axial thrust will appear in the boundary conditions and the bending moment would be 0 at the free ends. Okay. This is the shear force at the two ends. Okay. So, I leave the intermediate steps for you to work out. So, now a beam carrying some inertial elements and a spring, this again helps you to appreciate different facets of this formulation. So, the kinetic energy now has contribution from this mass, contribution from this beam and from this mass m2. m1 and m2 are point masses. So, this is the expression for the kinetic energy. U of t is the displacement of this mass and V of x comma t is the displacement of the beam. The potential energy now has the one that is stored in the beam and the one that is there in the this spring, and we get this. So, now you apply the variational formulation, you will get one equation for u, another equation for v, and the equation for v reads as shown here, and the equation for u is this, and the boundary conditions at x equal to 0, we can see that bending moment emerges to be 0, but the shear force will have contributions from at this end from this mass, and at this end there will be a shear force contribution from this spring. So, these are the appropriate boundary conditions. Now, how about a beam with a overhang? So, there are now 3 places where we need to worry about the boundary conditions. So, what I do is I call displacement field in this portion as V1 and in this portion as V2, and we will assume that Ei and M are functions of x as x varies from 0 to L1 plus L2. So, the kinetic energy now has contribution from this segment of the beam 0 to L1 and L1 to L1 plus L2. Similarly, the strain energy flexure in this part plus flexure in this part. The action integral is now therefore T minus V is this expression. So, now I will take V1 to be a class of admissible parameterized admissible set of functions is formed by for both V1 and V2 as shown here. Okay. Now, so this is the action integral in terms of epsilon 1 and epsilon 2, and these are the conditions for stationarity of this. So, if we run through this calculation, you will have to do this differentiation and the corresponding integration by parts, and if you carry out these calculations, we get the field equations for x varying from 0 to L1 and x varying from L1 to L1 plus L2 separately, and they are shown here. And now, the boundary conditions, you will have to consider what happens here, what happens here and what happens here. So, the required conditions of compatibility and equilibrium of forces etcetera is automatically satisfied in this formulation, and we get I mean you can go through these steps, these are simple manipulations, and we get the boundary conditions as shown here. So, this is at x equal to 0, bending moment would be 0 and displacement would be 0. Here the bending moment would be 0, shear force would be 0. Here what happens? So, at x equal to 0, these are the boundary conditions. At the x equal to L1 plus L2, that is the right hand free end, this is the bending moment and shear force are 0. At the intermediate point, this is the equilibrium of moments, and this is compatibility, and V1 and V2 must be equal to 0, right. So, we have now 8 boundary conditions and 2 fourth order equations, and along with that we should specify the required 4 initial conditions. So, this gives a formulation for a beam with overhang. So, I suggest 2 exercises. You can consider a propped cantilever beam with a hinge in between. You now formulate the the equation of motion and obtain the appropriate boundary conditions. The other example is a beam that is spinning about this y axis. Okay. So, you have to correctly write the expression for kinetic energy and the energy due to bending and derive the appropriate field equations and boundary conditions. Now, at this stage it is useful to quickly review the solution of equation of motion for discrete multi-degree freedom systems. So, this is a generic form of equation of motion for linear systems, time invariant linear systems. Mx double dot plus Cx dot plus Kx equal to f of t. X is displacement vector, M is mass matrix, C is damping matrix, K is the stiffness matrix, and these are the initial conditions. Now, what I do not intend to do this review as a part of this course, because this review is already available in another NPTEL course which I have taught, and this is the website where this is available. And if you go to lecture 13 slides 3 to 50 and lecture 14 slides 2 to 24, you will get this review. So, I will assume that when you reach this point, you will go to these lectures and familiarize yourself with the contents of this lecture before proceeding further as a part of this course. Similarly, in the same course that I mentioned, in lectures 15 and 16, there is a review of solution of equation of motion for continuous multi-degree freedom systems, specifically in the context of an Euler-Bernoulli damped Euler-Bernoulli beam, and all the steps involved are again completely outlined here. They run over two lectures, lecture 17, 15 and 16, and these are the slide numbers. So, again I presume that before you proceed further in this course, you will visit these two lectures and familiarize yourself with the contents of those lectures. Now, the next topic that I would like to discuss is known as Rayleigh's quotient. Now, the strategy that we are using right now is we want to first outline what are the approximate methods for analyzing vibrating systems, and we will outline a few methods, and that will lead to that will provide the motivation for us to understand how the finite element method is developed. So, as a prelude to that, we will start with what is known as Rayleigh's quotient. Now, if you consider a n degree of freedom system with mass matrix M and stiffness matrix K, where M is symmetric and positive definite, K is symmetric and positive semi definite, we will denote by omega I and phi I the ith eigenpair. So, these are obtained by solving the eigenvalue problem associated with these two matrices, and phi is the modal matrix. So, it is the matrix of the eigenvectors. So, this is a n cross n matrix, each column represents one eigenvector, and I assume that these eigenvectors have been normalized. So, that phi transpose m phi is an identity matrix, that means these normal modes are mass normalized, and phi transpose k phi is a diagonal matrix where the diagonal entry is omega I square. Okay. So, these are the orthogonality relations and the normalization conditions used. So, if you take now the nth eigenvalue and nth eigenvector, the equation that it satisfies is given by this. Now, if you pre-multiply by phi n transpose and on both sides, I get this equation, and K is a n by n matrix, phi n is a n cross 1 matrix. So, this will be a scalar because this is 1 cross n, n cross n, n cross 1, therefore, this is a scalar. So, I can divide write this expression for omega n square as phi n transpose k phi n divided by phi n transpose m phi n. So, this is an exact result. Okay. Now, instead of considering this nth eigenvector, that eigenvector I will now replace by an arbitrary n cross 1 vector. I form the ratio u transpose k u divided by u transpose m u. By definition, I call this quantity as Rayleigh's quotient. So, clearly we denote it as R of u, u is a vector, and it has clearly the units of radian per second whole square. Now, if u were to coincide with the nth eigenvector, R of u would be simply the nth natural frequency. Okay. Now, why we are interested in this quantity? This quantity has two important properties, namely this is bounded between the first natural frequency, first eigenvalue and the last eigenvalue, and also the second property says if u is in the neighborhood of phi n, if u is phi n plus epsilon y, where y is a vector which is a perturbation, R of u, which is the eigenvalue, will be in the neighborhood of omega n square, but this correction is order epsilon square. The error in the vector u, the error I mean the departure from the true eigenvector, if it is order epsilon, the error in the eigenvalue will be of the order epsilon square. So, this helps us to evaluate the eigenvalues in an approximate manner by making guesses on the eigenvector. So, if you make an error of order epsilon in making the guess, you will end up with an order epsilon square in your estimate of the eigenvalue. So, this is an advantage. So, we will see this with a few examples, and also I will now show why those two statements are true. Actually, the main application of Raleigh's quotient is that it can be used to approximate the first natural frequency of the systems by making guesses on the mode shape. That means, we are going to use this part of the result. So, if my objective is to estimate the first natural frequency, I will start by making a guess on the first mode shape and substitute that in this expression, and I will get an estimate for the first natural frequency. Okay. Now, we will see that through an example. Suppose if you consider now a 3-degree freedom system, and these are the parameters. You can easily write the equation of motion. So, this is the equation of motion, this is the mass matrix, this is the stiffness matrix, and if you carry out the eigenvalue analysis, you will see that the modal vector is modal matrix is given by this. This is the diagonal matrix of squares of natural frequencies, and this modal matrix is mass normalized, you can verify that, and the phi transpose k phi is nothing but this lambda. So, this is an exact result. Now, if I now make a guess u, for example 1 1 1, what will be R of u? You can compute that. That means, I am assuming actual mode shape, if for example is 1.13, 1.63, 1.78. So, what I will do is I will take that as 1 1 1. So, that is a guess on my mode shape. Then my approximation to the R of u turns out to be this number 22.22. So, this is if you are interested in estimating the first natural frequency, this will be the your estimate of the square of the first natural frequency. If you take something like 1 2 3, right, this will be the estimate. On the other hand, if you take say 1.1, 1.62, you come closer to the true natural frequency. Now, if you take 1 minus 1 minus 1, this will be a bad guess on the mode shape. If you are familiar with how mode shapes behave, this will not be a good guess on the first mode shape. Therefore, this is depicted in the Raleigh's quotient. But no matter what you are doing, we see that Raleigh's quotient is bounded between the first natural frequency square and the last natural frequency square in all these examples. Now, among these various trials on your guesses on the first mode shape, this one gives the lowest Raleigh's quotient. So, if you actually in this case I know 17.25 is the answer, but if you are applying this method under a situation where you do not know the exact answer, you should accept this as the best possible approximation to the square of the natural frequency because of this bounding property. R of u can at best be only equal to the first natural frequency square, it cannot drop below that. So, because of that bounding property, the lowest among this is the best possible estimate for the first eigenvalue. Now, why this bounding occurs? First I will give a physical explanation and then we will work through the mathematics of it. Suppose for this system, this is a schematic, it is not a sketch drawn to the scale. Suppose this is the true mode shape. Now, if I make this as a initial guess, to maintain this as a normal mode for the system, I should supply additional forces which bring back this point here, brings back this point here, this point to this. You will be supplying additional forces to the system and that does additional work and that contributes to the potential energy. So, therefore, the natural frequencies go up. Okay. So, to maintain the approximate mode shape, we need to apply additional forces and this leads to increase in the potential energy of the system, which in turn increases the natural frequency. That explains why the Raleigh's quotient provides the bound. Now, we can quickly argue out why these results are true. So, I will start with the first result that R of u is bounded between first natural frequency and the highest natural frequency. How do I show that? Now, u is a vector, n cross 1 vector, therefore, it can be expanded in terms of these true mode shapes. So, I can write u as a linear combination of these mode shapes, where alpha n takes value from 1 to capital N. Now, using this R of u can be written in this form. Now, since phi n's are true mode shapes and they are orthogonal with respect to k and m, okay, and they are mass normalized. If you expand this out, all the this will become a double summation, but all the cross terms will go to 0 and I will be left with this in the denominator. Similarly, in the numerator the diagonal terms will have omega n square multiplying alpha n square. So, this will be the Raleigh's quotient in terms of the unknown true natural frequencies and these unknown alpha n's. Now, I will manipulate this. What I will do is I will expand this is and pull out omega 1 square outside. So, first term will be alpha 1 square as it is, omega n square has gone outside and this is other terms are this and the denominator remains the same. Now, there is an ordering of natural frequencies, omega 1 is less than or equal to omega 2 less than or equal to omega 3 and so on and so forth. That is how the labels on eigenvalues appear. So, consequently, we can see that these terms inside the bracket here will be greater than or equal to 1. So, consequently, we see that this inequality holds. Okay. Now, to get the other bound, what I will do is now I will pull out the last frequency outside and divide by omega n square all other terms. So, this will be this multiplier will be 1. Now, by the same logic now all these numbers inside this bracket will be less than or equal to 1. So, consequently, this bound emerges. So, we get this result that Raleigh's quotient is bounded between first eigenvalue and the last eigenvalue. Now, we can work through this if the u that we are selecting is orthogonal to the first s modes. It so happens that you know first 3 modes and you select the in a 10 degree freedom system, for example, if you select your trial function to be orthogonal to the first 3 modes, then you will end up getting an upper bound on the fourth natural frequency. So, that is the third natural frequency, that is this result can be shown using similar arguments. I leave this as an exercise for you to complete. The second result that I stated has this notation order epsilon square. Okay. Now, what I want to do is first I want to define what exactly is this notation means. So, we will see that first, then before going to the proof. So, we use what are known as the capital O and lowercase o notations. Now, if we consider a function f of x and if we say that it is order g of x as x goes to a, what it means is if x of a is in the neighborhood, x is in the neighborhood of a by this distance delta, then this f of x will be less than or equal to this m into g of x, where for every a there exists a m greater than 0 and delta greater than 0. So, that this inequality holds good. Operationally, to verify that, what we need to do is we have to divide f of x by g of x and take the limit x tending to a. If this is finite, then we say that f of x is order g of x at as x goes to a. The lower case order g of x means this actually goes to 0, it is not just finite, but it actually goes to 0. Okay. Now, some few examples. For example, we have this ax to the power of 7 plus bx cube plus cx plus d. The question is it order x to the power of 7 as x goes to infinity? How do I verify? I will form this ratio and you can see that this first term will be a and all this will be 1 by x to the power of 4 etc. As x tends to infinity, this goes to a, it is finite, therefore, this is true. Now, is this order x to the power of 0 as x goes to 0? Again we see this as x goes to 0, all these terms will drop off, there is a d here which is finite, therefore, this is also true. So, ax to the power of 7 is order x to the power of 7 by this logic again, whereas ax to the power of 7 is not order x to the power of 8, because this will be 1 by x and as x goes to 0 this becomes unbounded. A few more example, sin x is order x as x goes to 0, because sin x by x as x goes to 0 is 1, which is finite. Similarly, sin x square is order x square because of this identity. So, there are a few more examples you can verify, and this order notation we will be using soon in this part of the lecture, but later on when I come to numerical integration of equilibrium equations, I will be using these notations again. So, that is why I have introduced at this stage. Now, what is the result that we are talking about? if u is in the neighborhood of the true nth eigenvector and the departure is epsilon y, that is order epsilon y, order epsilon, then the Raleigh's quotient will be omega n square plus order epsilon square. So, how do I show that? So, you can again write R of phi n plus epsilon y, you write this and you expand this, and phi n is a true mode shape, therefore, it will satisfy the I know this is the square of the natural frequency and this is 1. So, that is what I write and I am left with these two terms. Now, this y is the perturbation. Now, I will take y to be in terms of all the modes except the nth mode, that is how we can write this. So, if you now substitute this, we can show that phi n transpose k y is 0, because every we are excluding I not equal to n, that is 0, and phi n transpose m y is 0, and this is 0, and we get y transpose y as this, which is this is here, and y transpose k y, y transpose m y is here, y transpose k y is here. The term I not equal to n, in this summation I cannot take value of n. Now, if you go back and substitute, you get this ratio, and the denominator I can write in this form, and if I do a binomial expansion of this and retain only the first few terms, I get this expression, and we can see that the Raleigh's quotient is possesses the property that I stated. That means, this term is order epsilon square. Okay. So, if you make a reasonably good guess on eigenvector, you will get reasonably good, much better answer on eigenvalue. That is the story. So, this also means that this Raleigh's quotient has a stationary value in the neighborhood of an eigenvector. It indeed takes the minimum value in the neighborhood of the fundamental mode. This result, this is known as Raleigh's principle. Okay. Now, this will be useful in some of our formulations. Now, the discussion on Raleigh's quotient can also be based on a slightly different argument, and that is based on energies. So, if I now consider, for purpose of illustration, I will consider a simple system, a mass spring system. There is no energy dissipation here, therefore, it is a conservative system, the total energy is conserved. So, this is the expression for kinetic energy, this is the expression for potential energy. If I add these two energies, I get the total energy, which must be a constant, because there is no energy dissipation in the system. Now, in normal mode oscillations, we are interested in harmonic oscillations. So, in a multi-degree freedom system, we say that a system is executing normal mode oscillations if all points on the structure are vibrating harmonically at the same frequency. So, in this case, it is a very trivial case. So, if it is executing harmonic motions, u of t will be given by this. Now, let us substitute this into the expression for kinetic energy. I get kinetic energy to be mA square omega square by 2 sin omega t, sin square omega t, and this is cos square omega t minus alpha. Now, total energy is sum of this. If you add now this sin square and cos square will add up, and I get this is a constant that I am talking here. Now, this would automatically means that when kinetic energy reaches its maximum value, the potential energy must be 0, and similarly when potential energy reaches its maximum value, the kinetic energy will be 0. So, if we write that, you can see here the expression for kinetic energy has sin square omega t minus alpha, the potential energy has cos square omega t minus alpha. The maximum value that function sin square omega t minus alpha can take is 1. Similarly, cos square omega t minus alpha, the maximum value that this function can take is also 1. So, I get the maximum kinetic energy to be this, maximum potential energy to be this, and since they are equal, I get the expression for the natural frequency. So, I have been able to write this expression for the natural frequency without writing the equation of motion. I am simply using the fact that I am looking for harmonic oscillations, harmonic oscillatory responses, because that is how we define the normal mode oscillations. Now, how about the similar argument for a multi-degree freedom system? So, if u dot is the velocity vector, m is the mass matrix, we can write the kinetic energy as half u dot transpose mu dot and potential energy as half u transpose ku. The total energy will be the sum of these two, and again this must be a constant. In normal mode oscillations, all points on the structure vibrate harmonically at the same frequency. This is the amplitude of those oscillations and this is the frequency, and this phase difference could be either 0 or pi in an undamped system. That means it is a synchronous motion, all points vibrate harmonically at the same frequency, so that the ratio of oscillations at any 2 points is independent of time. That also means all points reach their respective maximum values simultaneously, maximum and minimum values simultaneously. That means phase is either 0 or pi. That means points can be perfectly in phase or perfectly out of phase. There is only 2 phase differences possible. Now, for this type of motions, which are the normal mode oscillations, I can write the kinetic energy. This is given by this, potential energy is given by this. Now, the maximum value of kinetic energy is reached when sin square omega t minus alpha is 1, that gives me this, and maximum potential energy is reached when cos square omega t minus alpha is 1, that gives me this expression. So, if I equate these two, I get the expression for omega square, which is the u transpose ku, u transpose mu, and now you will recognize that this is nothing but the definition of Rayleigh's quotient for a trial vector u. Okay. Clearly, when u coincides with the true natural frequency of true normal mode of the system, this will be the corresponding natural frequency or the corresponding eigenvalue, which is square of the natural frequency. Now, how about for a continuous system? Now, let me consider this axially vibrating bar. U of x comma t is the axial displacement, L is the span, A is the axial rigidity, m of x is the mass per unit length. So, we have derived these expressions for kinetic energy and potential energy, which is strain energy. So, again in normal mode oscillations, all points on the structure vibrate harmonically at the same frequency, and phi of x is now the eigen function, which is not known. Okay. So, now I will substitute this into the expression for kinetic energy, and again notice that the maximum value will be reached when cos square omega t minus alpha is 1 and sin square omega t minus alpha is 1 respectively for the potential energy and the kinetic energy. I will get maximum kinetic energy to be this and maximum potential energy to be this. So, these two need to be equal. So, based on that I get now the expression for the frequency of oscillation, and this is defined as now the Rayleigh's quotient for axially vibrating bar. Now, unlike in discrete multi-degree freedom system, this Rayleigh's quotient here only satisfies the bound at this end, because the highest natural frequency of a distributed parameter system goes to infinity, there is no bound on this side. It virtually means the Rayleigh's quotient is less than infinity, but that is not worth stating. So, we only get bound on one side. How about the Euler-Bernoulli beam? Again we consider this beam system, L is the span, EI is the flexural rigidity, m of x is the mass per unit length, and displacement in the y direction is v of x comma t. So, this is the expression for kinetic energy, this is the expression for the potential energy. Now, in normal mode oscillations again we take the response to be phi of x cos omega t minus alpha. So, this is the expression for the maximum kinetic energy, this is the expression for maximum potential energy. These two must be equal. So, I get the definition of Rayleigh's quotient for a beam in terms of flexural rigidity and mass per unit length as shown here. Again we notice that the Rayleigh's quotient is greater than or equal to omega 1 square. So, in the next class what I will do is I will apply this idea of Rayleigh's quotient for a few class of systems and show how it is useful in characterizing the natural frequency of obtaining approximation to the fundamental mode of vibrating systems. Now, the success of this quotient, Rayleigh's quotient as an approximation to the first eigenvalue, depends on how well you can approximate the mode shape. So, it is not always that you can make intelligent guesses, right. So, you need to have a systematic procedure to lower the Raleigh's quotient. Now, how do we lower the Raleigh's quotient? So, to be able to do that, we should introduce certain undetermined parameters in my definition of the trial function. This is the assumed mode shape. So, if I assume phi of x as a series, if I do expand this unknown trial function in a set of say orthogonal functions with unknown undetermined coefficients, then I can select those undetermined coefficients so that the Raleigh's quotient is minimized, right. So, that gives us a systematic way to lower the Raleigh's quotient and therefore obtain better approximation to the first natural frequency. Now, in doing so, we not only get a better approximation to the first natural frequency, but we will also end up getting approximations to the higher natural frequency. This method that I am talking about is known as Rayleigh-Ritz method. So, in the next part of the lecture, after illustrating the applications of Raleigh's quotient, we will develop the Rayleigh-Ritz method and then again apply to a few methods. I will conclude this lecture at this point.